In this video, we're going to do an introduction to trees. So the concept of trees has a lot of wonderful applications used in computer science. So let's do some terminology. First of all, let's define a tree. A tree is a connected, undirected graph with no simple circuits. So connected, that word means that we can get from any vertice to another, to all the other vertices. That's what makes them connected. And then a circuit is when a path completes, right? We get back to what we started with. So let's look at this example here. Let's figure out which ones are trees, and let's start by figuring out which ones are in fact connected. That doesn't look like a C, but it's supposed to be connected. There we go. All right. So starting with the first graph, if I start at A, I can get to B by just going along this path. I can get to C by going here. I can get to D by going a little further. I could get to E by going down this way. And then of course I can get to F by just going right there. Okay, cool. And if I do that with any of the vertices, they're all going to work. So this is so small, I'm sorry, but it does say G1 underneath. It's hard to see, but that's G1, G2, G3, G4. Wow, it's really tiny. All right, let's look at the next graph. Again, I'll start at A and see if I can get to B. Okay, so to get to B, I actually have to kind of go quite a long way. I have to go down here and then there. But I do it. I got it to B. All right, let's try going to C. Oh, wait, that's easy. C is easy. D, I would have to go here. To get to E, I would have to go this way. And then to get to F, just right there. Oops. So G2, that one's connected. All right, let's look at G3. And again, you have to kind of make sure you can do that with all of them. But really, when you kind of exercise it with one, it helps you see. All right, G3, let's see. If I want to get to B, I go here. If I want to get to C, I would go here. D is right along here. E, I could get two different ways to E. All right. And then to get to F, I would need to go this way. All right, cool. So G3 is also connected. And then G4, actually, I can already tell. G4 is a problem. A is only connected to F. There's no way for it to get to any of the other vertices. So it's not connected. G4 is not a tree. All right, now I just have to look for circuits. I have to make sure that there are no simple circuits. And the one I'm actually most interested in is G3. So let's look at this particular circuit here. I'm going to write it out and then we'll map it. So I have, oops, sorry, simple circuit. Okay, so on G3, if I go from E to B to A, D, back to E, that's a simple circuit. So E to B, B to A to D, back to E. So that one forces me, that path forces me back to E. So that circuit is the problem with G3, which means that the only two trees here are G1 and G2. Oops. Okay, so that's how we can tell which ones are trees. A forest is a graph that has no simple circuits, but is not connected. All right, each of the connected components in a forest is called a tree. So as you can kind of see here, this is actually one graph and it has these three connected components, but because it's one graph, that makes it not connected all together since there's three kind of individual pieces there. All right, so let's look at our first theorem. An undirected graph is a tree if and only if there is a unique simple path between any two of its vertices. And that makes sense because really the problem is that on the graph that ended up having a circuit, there was a couple options to get to E, and that's why we had a circuit. Okay, we had a couple ways we could get from A to E. We could go down the path for D, right? We could go this way, or we could go the path through B and get to that way. So we had multiple ways that we could get there, and that is why it has a circuit. So this basically says if we have a unique simple path, we're good to go. I'm not going to prove that. We will be looking at some proofs later that we're going to prove. But before we do that, let's just kind of move into some interesting notes. So trees are used in computer science, chemistry, geology, botany, psychology, so many places. They were first introduced by the mathematician Cayley in 1857, and he was doing work on isomers of saturated hydrocarbons. Wow, use that in a sentence today. You'll feel so smart. And as you can see, these were two of the mappings that he had done, and it kind of led to these ideas of trees. It's used in even businesses, like you can do subcategories or hierarchical of the jobs. Or in this case, they're showing what it could look like in a computer file system, what that system might look like. It is, in fact, a tree. Okay, so the next group of terminology we want to kind of look at is a rooted tree. So a rooted tree is a tree in which one vertex has been designated as the root, and every edge is directed away from the root. An unrooted tree can be converted into a rooted tree when different vertices are chosen as the root. Okay, so here's our tree T. That's the one on the left. And if you choose A to be the root, you can create a rooted tree and you path it. So you'll see that this path, when we go from A to B to F, that happens to be boop, right there, that path. All right. Or to G, we would go the other part of that little fork. So all of this is choosing A to be the root. Let's draw one. Let's choose the root to be C. Okay, so C is going to be our root. So C can map to either A or E. I'm going to kind of just go alphabetical order here. So A will go here. E will go here. All right, and then E is a dead end. It's done. So really the path is now going to go along A. All right, so for A, here I want to give myself a little space. For A, we're going to path, we could go to either B or D. All right, but D is a dead end. So that one's done now. Then from B, we can either go to F or G. And again, I'm using alphabetical order to kind of help me decide which one to write first, the left or the right. And there is some distinctions between left and right. We'll talk about that in just a little bit. But there you go. That's how the rooted tree would look like when we choose the root to be C. All right, let's look at more vocabulary. Now, this vocabulary is kind of funny. It uses like a mix of botany and genealogy to kind of talk about paths and different relationships between vertices. Okay, so a vertex is a rooted tree other than the root. If a vertex, V is of a rooted tree other than the root, then the parent of V is the unique vertex U, such as directed from U to V. So the idea of parent meaning like if a vertex is lower, not in the root, like B, right? The parent would be A. Okay. And here we'll see some examples in a second. Then there's the idea of a child, the other direction. Siblings, that's when they're connected to a vertex. Ancestors are all the vertices that happened previously, and then descendants are all the vertices that are to come. Okay, now this terminology is actually probably the most important for us. Vertex of a rooted tree with no children is called a leaf, and vertices that have children are called internal vertices. So we'll be referring to that quite a bit later. Let's just kind of make sure we understand parent, sibling, child, ancestors, descendants really quick. Oh, here's a nifty example. Sorry. If a vertex in a tree, the subtree with A as its root is the subgraph. So it's possible to have a subtree and subgraphs. And as they actually literally did a family tree to demonstrate this. Parents, descendants, ancestors. It's kind of nice. Siblings. It all kind of connects to exactly even just a family tree. All right, here, let's dig into all this terminology and make sure we understand it. So find the parent of C, the children of G, the siblings of H, the ancestors of E, and the descendants of B. Okay, so let's do that here. I'm going to give myself a little space. So let's start with the parent of C. So C is right here. Its parent then would be B. Parent of C is B. Okay. Then we're going to look at children of G. So going to G, it has, so children of G would be Hij. Hij. So all three of those would be children. Okay. Siblings of H. Siblings of H. Okay, so here's H. So those are people, wow. Those are vertices that are connected to the same parent. So I and J would be siblings. Oops. Comma J. All right. Ancestors of E. Okay, so E is down here, and that would be basically every vertice connected to E backwards. So C, B, and A. And then descendants of B. So these are all the ones that path downward. So here's B. Descendants would be C, and then two children off of C. So D and E, all of those are C, D, E. Okay. B, let's find the internal vertices and leaves. So internal vertices means they have children. Leaves do not have children. So internal vertices. That would be, okay. So A would count, it has children. B would count, it has children. C would count as well, it has children. G would count, H would count, and J would count. And the rest are going to basically be the leaves. So A, B, C, G, H, J. Okay, so leaves are then D, E, F, I, K, L, and M. All right, and then for C, what is a subtree rooted at G? Okay, so actually I'm going to draw that. A subtree rooted at G means that we're going to just take what happens at G. So G is my root, and what happens there is it branches off to I, H, and J. So this one's H. Here's I, and then J. And then H branches down to K. I's a leaf, so it's done. And then J goes to L and M. So that would be how you would draw a subtree. You literally just taking part of the tree and only looking at part of it. All right. A rooted tree is called an M-ary tree if every internal vertex has no more than M children. The tree is called a full-ary tree if every internal M-ary tree. I said Mary, sorry. If every internal vertex has exactly M children. An M-ary tree with M equals 2 is called a binary tree. All right, so it's the idea that you're counting how many branches off for each parent. So how many children there are. All right. Let's look at this example. How many of rooted trees are full M-ary trees? And then we're going to figure out, if we can, what M is for each of them. So let's look at T1. So T1 starts off where we branch into 2 children. And then this one branches into 2 children. And then this one branches into 2 children. Okay, so here, that's an example of a full binary tree. Because everybody that has children has 2. So M is 2 in this case. All right, let's look at T2. So in this one, we start off with 3. This one has 3. This one has 3. And this, okay, again, everybody that has children has 3. So that would be a full 3-ary tree. So that's how we say that. T3. So this time, 1, 2, 3, 4, 5. This one has 1, 2, 3, 4, 5. And this one has 1, 2, 3, 4, 5. So again, full 5-airy tree. All right, for the last one here, we start with 2. Okay, but now we went to 3 on both of those and then back to 2. So this is not a full tree. All right. Well, if to label this, we would call it a 3-airy tree, but not full, because an M-airy tree is that they have no more than M children. So nobody has more than 3 children in this tree. So it's a 3-airy tree, not full. All right, so there you go. An ordered rooted tree is a rooted tree where the children of each internal vertex are ordered. We draw it so that they are shown in order from left to right. And I mentioned left to right earlier. So here, let's look a little bit deeper here. A binary tree is an ordered rooted where each internal vertex has at most 2 children. If an internal vertex of a binary tree has 2 children, the first is called the left child, the second is called the right child. The tree root at the left child of the vertex is called a left subtree, and the one at the right is the right subtree. Okay, so let's look at this. Okay, so what are the left and right children of D? Okay, so going to D, oops, right there. The left one would be F, the right one would be G. So left child of D is F, right child of D is G. All right, part B. What are the left and right subtrees of C? Well, actually, that's displayed here in the other 2 graphs. So for C, the left subtree is displayed in the graph B here, this one. And then the right subtree is displayed in the graph C, because those come off of C, and it has this graph, and then it has, I'm sorry, it's tree, it's subtree, and this subtree. So there's the left subtree and there's the right subtree. And I'm just individually drawing those, but they had it already drawn, so we grabbed from it and we moved on with our lives. All right, let's move on here. So first of several theorems we're going to look at, they're actually not too bad. A tree with n vertices has n minus 1 edges. It's actually kind of very logical when you think about it, but let's do a proof by induction, and it's not too bad at all. So we'll start with the basis step. So the basis step, oops, is when we show that it's true for n equals 1. So this is true for n equals 1, since a tree with 1 vertice or 1 vertex, because you wouldn't say vertice, you would say vertex since there's only 1. 1 vertex has no edges. And according to the theorem, this would have 1 minus 1 edges. So done. All right, induction step. Okay, so here we're going to assume that every tree with k vertices has k minus 1 edges. All right, now we'll look at a tree with k plus 1 edges. So consider the tree, we'll call it T, with k plus 1, not edges, sorry, vertices. Now, if this is right, we should come out with k edges, okay, if we did it correctly. All right, so here's how we do this. Let V be a leaf of T. So remember, a leaf means it's an end point. It stops, has no children. Okay. Let W be the parent of V. Okay, so we backtrack to the parent. So removing the vertex V, if we get rid of V, and the edge, from W, or let's say to W, that produces a brand new tree which we'll call T prime. All right. And T prime has K vertices because I just took one away. It had K plus 1, now it has K. So by assumption, what I assumed earlier, T prime has K minus 1 edges. Since T, the original tree, has one more edge than T prime, then T has K edges. And we did it. There it is. All right. A full M-ary tree with I internal vertices has N equaling Mi plus 1 vertices. Okay, so remember, I'm just going to state this really quick. Remember that T is a full M-ary tree. What that means is, means that each internal vertex, those are the ones that have children, each internal vertex has M children. That's what it means to be a full M-ary tree. Oops. All right, so keeping that in mind, the proof is pretty simple. Every vertex except the root is the child of an internal vertex. Because each of the I internal vertices has M children. There are Mi vertices other than the root. But now, if we count the root, with the root, there are Mi plus 1 vertices. And we're done. All right. Another theorem here, but I'm not going to go through the proof. You can look at the proof, but it gives ways of calculating the internal vertices for a regular M-ary tree, the leaves, and just various pieces of information based on knowing that we're working with a full M-ary tree. All right. We're not going to go through that. Just put that in there. One thing we do want to kind of understand is some more language where we talk about level versus height. So the level of a vertex, V in a rooted tree, is the length of the unique path from the root to this vertex. All right. So we're talking about how we path up to the top. And then the height is the maximum of the levels for the vertices. Let's look at this by example. It's actually pretty straightforward. So A, the first vertex, would be what we call level 0. All right. B and J, B, J, and K would all be called level 1. So they're all one path away from A. Level 2 would be C, E, F, and L. Level 3 would be D, G, I, M, and N. And then we have one item at level 4, and that's H. Okay, so for part B, the height of this tree is 4 because we go based off the biggest level, the lowest level. All right, rooted M-ary tree is balanced if all the leaves are at levels H or H minus 1. Okay, sorry, I didn't say that full definition. A rooted M-ary tree of height H is balanced if all of the leaves are at either H, levels H or H minus 1. All right, so it's the idea that we don't have too many short leaves that are kind of hanging off all very lot shorter than everything else. So as you can see in T1, there are a couple leaves that stop short, but since the longest height, or I should say the lowest level, so 1, 2, 3, 4, all right, that's level 4. Those two both stop at level 3. So this one is what we would consider balanced. The two leaves are only one level short of the rest. T2 is not balanced because this one and this one are 2 levels short of the lowest levels. So not balanced. And this one is definitely balanced. Everything ends up being at the same level. Those leaves all ended up being at the same level. All right. Now this theorem, I went ahead and included the proof. We'll just kind of chat about it for understanding's sake, and then we'll look at its corollary. So there is at most M to the H leaves in an M-ary tree of height H. So they use induction to show this. Basically, if you're looking at an M-ary tree of height 1, that's a tree that consists of a root, no more than M children. They're all leaves. Therefore, they're exactly M to the 1 leaves away, or a height of 1. All right, that's pretty straightforward. The induction step basically takes, we make our assumption that an M-ary tree of height H that has it at most, assume the result is true for M-ary trees less than height H. Okay, so they're actually going below height H. Okay, so that would mean that according to that, we're assuming they have at most M to the H minus 1 leaves. All right, then basically what we do is we take one of the leaves and we track it backwards. We end up kind of removing the leaf and being able, kind of what we did earlier, where we kind of removed it and were able to do the counting. And that's basically what they did. They have this kind of diagram to spell that out. I'm not going to really get into it. We do end up getting a corollary from this about the way of calculating the height based on a logarithm, which makes sense when we're saying that the number of leaves can be based on the height. So if we want to define the height, we can use the number of leaves to help us do that. And that are trees.